Hello and welcome to the YouTube channel of Canara Engineering College, Bantwal. In today's video session, we will check regarding the applications of operation amplifier or what we normally call as opamps. So basically, we need to check out what is an opamp or how does an op-amp work or how actually an op-amp looks like. So in order to define an op-amp technically, op-amp is a direct coupled high gain, high bandwidth differential amplifier with very high value of input impedance and with very low value of output impedance. So how you can consider this particular op-amp as, you can consider your op-amp to be an amplifier, you can consider it to be an amplifier, and this amplifier is going to take the differential input in the sense, for example, if I'm going to give 5 volt from one terminal and if I'm going to give 3 volt from one more terminal, differential amplifier means this amplifier is going to take the difference of these two signals, that is 5 minus 3. So it is going to take 2 volt as input, and that 2 volt will be amplified by this particular amplifier as per the amplification factor. For example, if the amplification factor of this particular amplifier is 4, the output of this particular amplifier will become 2 into 4, which will be 8 volt. This is what is called as differential amplifier. Normally in case of your amplifiers, what happens, there will be one signal which will be given as input, and that signal will be amplified as per the amplification factor, and you will get the output. But in case of op amps, this op amp is a differential amplifier means it is going to take the difference of two signals, and that particular difference will be amplified as per the amplification factor, and that difference or the amplified value will be given as the output. And basically, when I speak about an op-amp, this op-amp has got high gain. High gain in the sense, I told you something regarding an amplification factor, right? Normally, the amplification factor of this particular op-amp will be comparatively higher when compared to your general amplifiers, which will be designed using transistors. So that is what it is says an op-amp is a direct coupled high gain, high bandwidth differential amplifier. So high bandwidth means normally the range of frequencies for which my op-amp will work is comparatively greater. This is what is called as bandwidth, right? You call it as cutoff frequency or something. F lower and F upper. F upper minus F lower will give you the cutoff frequency, and this is called as bandwidth. Normally the bandwidth region or the bandwidth range of this op-amp will be comparatively very high when compared to the normal amplifier. So that is what it says. It's an direct coupled high gain, high bandwidth differential amplifier with high value of input impedance, which means that the input impedance of this particular op-amp, that is when I give some signal to this particular amplifier, normally the input resistance offered by this amplifier will be comparatively higher. This is what is a general character what I expect from a very good amplifier. The input signal received by the amplifier should be very small. So if the input signal received by the signal should be very small, the resistance should be high, right? So this has got very high input impedance, and at the output side, the output impedance should be 0, which means that whatever signal gets amplified, that signal should be as such given to the output, isn't it? So this is what normally an op-amp means. So op-amp is generally a differential amplifier which has got very high gain, which works under very broad bandwidth, which has got very high input impedance, and which has got very low value of output impedance. The circuit diagram of your op-amp is can be seen here. So this is the internal schematic of your op-amp, which says that there is a supply, there is a positive and negative supply which is to be given, inputs to be given, and there are two transistors which are inbuilt, and outputs will be collected from the collector terminal of the transistors. This is a general indication of your op-amp. The symbolic indication is shown here. So you can see there are two terminals. One terminal is inverting and the other terminal is non-inverting. Also you can see it has got two supply voltages. One is plus VCC and other one is minus VCC, and one output terminal. So speaking about op-amp, you have a non-inverting input, inverting input. This is what I said, differential gain. So you can be giving the signal to the non-inverting as well as inverting input. That's what I explained here. You can give two signals and the difference of these two signals will be taken as input by this amplifier, and it needs two supply voltages, which is plus VCC and minus VCC. Along with that, it will be amplifying the signal, or the differential signal will be amplified and it will give the input. At the input side, the resistance will be comparatively high. High in the sense, it will be in terms of kilo ohms, it will be in terms of 10,000 ohms or more than that, which means that a very smallest of the smallest signal will be received at the input side, and coming to the output side, that is here, that is coming to the output side, the signal which will be given will be comparatively the same signal what has been amplified by this particular amplifier. This is the basics of your op-amp. Now what we need to learn in this video session is, we need to check regarding the various applications which can be done using the op-amp. The very first application what we have is, we may be checking it for the relaxation oscillator, or we may be doing a split trigger circuit, or we may be going with a peak detector circuit. We have got n number of applications when we speak about the op-amp. But before getting to the application part of this particular op-amp, what we need to check out is, there is something called as ideal op-amp and practical op-amp. Normally when I speak about any electronic devices, you say this is my ideal characteristics, but practically those ideal characteristics will not be satisfied. A practical device will be somewhere very close to an ideal device, but not same to that of your ideal device. Very similar in case of your op-amp. We'll check the basic differences between your ideal and practical op-amp. So ideal op-amp and practical op-amp. So as I said, in case of your ideal op-amp, internal impedance or input impedance is infinite. I said you it will be in terms of something around, here you say it should be in terms of infinity, which means that no signal should be received. Whereas practically, my input impedance will be ranging from 100 kilo ohm to 1000 mega ohm. As I said you, 10,000s of ohms. So this is where the practical value stands. We expect the output impedance to be 0, but practically output impedance cannot be 0. It will be very small, somewhere around tens to hundreds of ohms. Open loop differential voltage gain is infinite, which means that whatever signal you give as input, that signal should be amplified infinitely. That is what I expect from an ideal op-amp. But coming to the practical op-amp, open loop gain will not be infinity. Open loop gain will be somewhere in terms of 10,000 to 100,000, which is comparatively very high when compared to your normal voltage or normal amplification factor. Bandwidth is infinity. Bandwidth is infinity means I expect my op-amp to operate for all frequencies, for almost from 0 to infinite frequency. But in case of the practical op-amps, the bandwidth will be limited. The bandwidth is not infinite, it is limited. DC input and output offset voltage is 0. When I speak about DC input voltage, DC input voltage is the voltage that can be applied to the op-amp in order to make the output 0. DC input offset voltage can be defined as the DC voltage what will be applied at the input side of the op-amp in order to make the output voltage 0. Similarly, output offset voltage is nothing but the output voltage that is obtained from the op-amp when the input is grounded. So this is what is the definition of your DC input and output offset voltage. We expect both the offset voltages to be 0, but practically it has some finite values. It cannot be infinite. It cannot be infinite. It has got, or it cannot be 0. Sorry, it will be having some finite values. And input differential voltage is 0. Whereas in case of the practical op-amps, we expect the differential voltage to be, or it will have some finite values. It will not be 0. So when I speak about input differential voltage, we expect normally the voltage what is applied to the op-amp to be 0, because I told you, right, in case of my ideal op-amps, the input impedance is infinite. If the input impedance is infinite, obviously the input differential voltage will become 0. But when coming to the practical side, it will not be 0, it will be very high. So because of this high values, the differential voltage will also be very small. It is not practically 0. So you need to remember this particular 5 points. This particular 5 points are very important from the examination point of view, because they might ask you to quote the differences between ideal op-amp and practical op-amp. So this table has to be remembered by you people. Moving on further, launching on directly to the application part, the very first application of my op-amp circuit is peak detector. So what is this peak detector? Let us say I have a waveform, okay? Let us say I have a waveform something like this. I have a waveform something like this. So this is 1 cycle, 2 cycle, 3 cycle, 4, 5, 6 cycles. So now what you want is, you want to find out the highest positive value of this particular waveform. The highest positive value of this waveform is actually this one, is actually executed by this waveform. So you want to find out what is the highest value of this particular waveform. So the circuit which will be helping you in knowing the peak value of the waveform, it may be a sine wave, triangular waveform, square wave, or any waveforms, or it may be an irregular waveform also. Out of the waveforms whatever appear, if you want to find out the peak value of that particular waveform, then you can utilize or you can use peak detector circuit. So peak detector circuit is a circuit which will detect the peak of the waveforms. Out of all the waveforms, whatever is having the highest value, that peak will be detected, and that peak value will be displayed to you at the output side. So how does the circuit looks like? As I said, it's an application of your op-amp. So we employ an op-amp. Our output of the op-amp is connected directly back as input. So I can say this uses a negative feedback. This particular circuit uses a negative feedback. Basically, if the output is connected back to the input, we normally call it as a voltage follower circuit in terms of your op-amp, which is not a part of the syllabus. So let us say that you use an op-amp and the output is connected back as input to the inverting terminal of the op-amp. So I can say that it is using negative feedback. The voltage source or the waveform whose peak has to be detected is applied to the positive or non-inverting terminal of the op-amp through a diode. Through a diode you are applying it, and the diode path is bypassed by a capacitor and with the help of a switch. So this is the circuit description of your peak detector circuit. So it should be having an op-amp, it should be having a negative feedback, it should be having a voltage source, and on the path of the voltage source which is getting connected to the peak detector circuit or to the non-inverting terminal, you employ a diode and you employ a capacitor and a switch. So let us say this is the waveform what is getting applied to the non-inverting terminal of the op-amp. So what happens is, during the, please concentrate, during the positive cycle of the waveform, the diode will be forward biased. During the positive cycle of the waveform, the diode will be forward biased, and whatever voltage gets applied here, your capacitor will start to charge. Your capacitor will start to charge to the maximum value. For example, if you say that, let's say that you are applying only so much of the voltage, okay? You are applying only so much of voltage, that is whatever I am marking in red, only so much is getting applied to the capacitor, or so much is being given to the non-inverting terminal. So as soon as you start applying voltage, your capacitor will start to charge, and your capacitor will start to charge until this peak. Until this peak it will charge. It will charge to this peak. After that your voltage is going negative, right? Once the voltage goes negative, your diode will be turned off. Your diode will immediately be turned off, or your diode will be reverse biased. Once the diode is reverse biased, your capacitor voltage, or the voltage to which your capacitor has been charged, that will be applied to the non-inverting terminal of the op-amp, and that same voltage will be available at the output side, which means that this voltage will be available at the output side of the op-amp. Suppose if you apply, suppose you say that sir, here it is going positive, right? In this part it is going positive, right? Yes, in this part it will go positive. During this part of the waveform, your diode will be forward biased, but the capacitor will not discharge from this value to this value because this is the maximum value, right? So where the capacitor can charge again, the capacitor can charge again only if the value of the capacitor or only if the value of the waveform is higher than the value what is stored in the capacitor. Suppose here you say, sir, this is also positive going, right? Will my capacitor get charged to this value and this is not my peak? No. Once the capacitor is charged to the maximum value, once the capacitor is charged to the maximum value, it will not discharge. It will not discharge because your diode will be turned off, right? And next, it will charge only to the value which is greater than that, That is, during this peak, if you apply this voltage, your capacitor will charge to this value, and during this it will be turned off. It will be turned off. Again during this particular waveform, after this value or after this particular value, it will start charging to this value, and this value will be shown at the output side. Again during this path, your capacitor will remain idle. Your capacitor will not charge or it will not discharge because the value what is getting applied as the input to the capacitor will be less than that of the value what it is actually charged to. Finally, after this, it will start charging again and it will charge to this value, and this value will remain in the capacitor, and this value will get applied to the op-amp, and the same value will be shown at the output side. Which means that whenever the peak value occurs, that value will be, or that value of the voltage will be present in the capacitor, and the capacitor will give that as input to the op-amp, and the op-amp will be displaying the value. This is what is a peak detector circuit. So if you apply multiple waveforms having multiple peak values, then the highest of all those peak values will be displayed at the output side because you have capacitor there, right? So capacitor will charge first to the lowest peak. After that it will charge to the second peak. After that it will charge to the third peak. For example, if you say that, sir, my waveform is having the same peaks, sir. My waveforms is having all same peaks. Then it will charge to this value and it will remain idle because this value is equal to this one, right? Suppose if this value is greater than this value, then obviously your capacitor would have charged to this particular value. Now what has happened is the values are all equal, so the capacitor will charge to the same value, and that same value will be coming at the output side. Now if you ask me, sir, my capacitor will retain the value or retain that value permanently. Yes, that value will be retained permanently until you discharge that capacitor, and the discharging of the capacitor can be done using the switch what is connected across the capacitor. So once you say that my capacitor is containing this value, sir, how do I discharge it? I want to discharge my capacitor to 0. So normally you can discharge the capacitor by turning on this particular switch, and you can apply new voltage and you can start finding the peak of that particular voltage. This is what is called as peak detector circuit. In fact, this circuit has been modified in the next slide, and that is called as modified peak detector circuit. The same circuit has been modified here. The same circuit what we have studied has been modified, and you can check out. So here you have the input voltage what is getting applied, and this circuit is your voltage follower circuit. As I said you, this is your voltage follower circuit. Voltage follower circuit is the circuit which will give the output equal to the input. So whatever input you are applying at the input side, that same voltage will be applied at the will be coming at the output side. So you are applying the input voltage, that input voltage will be seen at the output side. The output voltage whatever I am getting here will be applied to the diode. So after this the circuit turns out to be the same. Right? And that voltage will charge the capacitor, and capacitor will be giving you the voltage what it is charged at the output side. And you can see here both the circuits are employing negative feedback. Here, and this diode is connected here just to make sure that your capacitor will charge to the positive peak, and the diode what is connected here, this is to make sure that your diode doesn't display the negative peaks, or negative peaks are not displayed by this particular diode, because you will have the positive as well as negative peaks, right? So in order not to show this particular values, I have connected a diode across here. Suppose if you say that, sir, if I want to find out the negative peak of the circuit, pretty simple. You just reverse this diodes. Whatever diodes you have here, you just reverse it. The diodes whatever I have connected here has to be reversed, and if you reverse the diodes, this diode will conduct during the negative cycle, right? And the capacitor will charge to the negative voltage, and that negative voltage will be available at the output here. And this will not let the positive voltage to be displayed at the output side of the capacitor. So this is the modified peak detector circuit. In fact, the circuit what I have here, the circuit what you are having here can be modified as per your requirement. In fact, the switch is missing here. You can connect the switch as per your requirement, and you can find out the peak of the voltages what you are applying at the input side. This is regarding the peak detector or one of the application of your op amp.